in this episode of the Critical Oxygen Podcast.
The whole reason the term is the nomenclature is oxidized is because typically oxygen is the final electron acceptor. And so it's like, oxygen stole your electron. You've been oxidized.
Hi, everyone. Welcome back to the Critical Oxygen Podcast, where we help you optimize your physiology and maximize your athletic potential. I'm your host, Phil Batterson, and today we're joined by continuing guest host, Dr. Robby Jacobs. Dr. Jacobs, welcome back to the show.
Thanks for having me back. I think I talk in different gradients of screams based on how excited I am. Mm-hmm. And I think when you talk to me, you kind of match me on that. And so when we transition from just chatting before we start the podcast to when you start, I feel like I'm especially yelling, and then you're like, "Hi, everybody. Welcome to the podcast." And I'm like, "Hey!"
You're just the Kool-Aid man busting down the door.
Yeah. Oh, yeah.
Oh, yeah. Already derailed. So I want to start today's episode with a question. A question I'm going to pose to you.
And what does she do?
No.
Oh.
No, that's for the end, remember? You got to...
Actually, have you ever seen Kindergarten Cop? I was stuck watching that when I was in the motel. Is that with
Arnold Schwarzenegger?
Yeah. It was pretty good. It's probably because it reminds me. But that's where it came from. Sorry, I derailed you again. Go.
What do you think the single most important molecule is for human performance?
The God molecule.
Which is?
I don't know, actually. I forget what I think it's the God particle. Oxygen.
Boom. Okay. So we're at least on the same page here. So I think both Dr. Jacobs and I agree that oxygen is probably the most important molecule for endurance performance, if not for life as we know it. And I start out with that question because I want to today set up this idea that oxygen is the most important molecule for endurance performance, and I want us to walk through how and why it's actually so important. This might be a bit of a philosophical, physiological, rabbit hole that we're going down, but I really think that a lot of people would gain a lot of benefit out of this. And again, continuing on with like the whole like origin story of the name of Critical Oxygen, I didn't choose Critical Oxygen just because I thought it was like,
it chose you.
Yeah, exactly. Like the logo chose me, like all that sort of stuff. So I didn't choose it because I was just like, oh, that's like just a cool name. It was,
although it is a cool name.
Thank you. I agree. It is amazing how much time and effort actually goes into determining like a company name, at least in my opinion. And I've had so many where I've oh, that's a pretty good name. I'll buy a website for it. I'll do all this other stuff, and then I'll be like, I'm not feeling the name anymore. And then it kind of takes the wind out of your sails. Critical Oxygen, though, the importance of this kind of came about when you and I were working together during my master's, and our first publication together, right? We started, or you had the theory, right, that that muscle oxidative capacity was the single best predictor of performance. You had showed that in one of your previous, research papers. And then we were building off of that. We said, hey, we have our traditional predictors of performance. There's also these predictors of performance that we can derive from NIRS. What do we actually, we hypothesized the entire time that those were the NIRS-derived oxidative markers were going to be better predictors of performance than the traditional predictors of performance. So, it's like, okay, that's all well and good. It's like, me being a naive master's student, I was like, yeah, that sounds about right. Like walking in and, kind of just like not blindly, but, like an educated but blind following naivete of following you and starting to think about this stuff. And then as we discussed mitochondrial physiology, I think in your skeletal muscle physiology class more and more, I started to actually appreciate and understand is like, okay, well, when you ask somebody, what do you know about the mitochondria? It's like 99.9% of the time, all you hear is mitochondria are the powerhouse of the cell. When I first heard that, so full disclosure, I never took a biology class in high school. So I never even got introduced to the mitochondria until like way later. So when people say the powerhouse of the cell, I wasn't even thinking about it as like the true powerhouse. Like I was like, oh, powerhouse. Like it's like, powerhouse, like flexing and stuff like that. My definition and my my connections were a little, wires were crossed. But then I was like, okay, well, if it's the powerhouse, it's what's generating the energy, right?
Or transferring the energy.
It's transferring the energy from, the power grid to your actual home itself, or your muscles. And then you have to start digging a little bit deeper and you say, okay, well, what's actually the driving force of that? And the paper that really stood out to me, and I mean, it's ancient now. It was published in 2018. But it's still probably one of the most relevant bioenergetics paper. It was a paper that was written by Dr. Daryl Newfer, who is, I don't know, arguably one of the best bioenergeticists, mitochondrial physiologists.
Yeah, I would say he's one of the preeminent names in human bioenergetics for sure.
Yeah. So if you've ever had the pleasure of hearing him talk, you probably understood about 10 minutes of his, it's because he's so smart. That he, it's like you understand about 10 minutes worth, and then you're like, oh man, I'm going to need to reread these papers and think about this a little bit more. So you and I just reread his Bioenergetics of Exercise paper that was published in Cold Springs Harbor Press. It's free for anybody to read, and I'll post a link in the show notes. And every time we read it, I think every time we read anything that's kind of poignant, we're like immediately texting about it. And what I want to do now is let's kind of set up, like the need for, say, energy, what's going on. I told you, I was like, every time I read this sort of stuff, I come away with it that the skeletal muscle is really dictating how our body is reacting to anything, or exercise in general, right? It starts at the skeletal muscle, and then we kind of, as you put it, have this Ouroboros where it's, a dragon eating its own tail. You start with energy demand, which essentially is related to oxygen demand. And then you go all the way around. There's all these stresses, all these different things. Your body reacts in order to try to maintain homeostasis, and then you have this kind of cyclic effect, going forward. So it's a long-winded way of saying, starts with oxygen. So if you want to give us, like your definition of why is oxygen so important, and then we'll kind of riff back and forth, I think that'll be a good starting point for people.
Sure. So anybody who's left their bike outside for too long realizes oxygen is corrosive, can be corrosive. It's because oxygen's unstable. Oxygen wants 2 more electrons. It's forever unfulfilled in its purpose in life. And to be fulfilled, it needs 2 more electrons. And that's why oxygen, molecular oxygen, doesn't exist. A single molecule of oxygen you don't really find in the environment because it's so unstable. It either exists as O2, where 2 molecules of oxygen bind with each other to kind of offset the need for those remaining 2 electrons, or you have H2O, right, for the 2 hydrogens. Well, that instability of oxygen sets the stage for energy transfer within the human body. Because ultimately, and this really blows my mind, I've probably read this paper 8 to 10 times, and every single time I read this paper, I walk away with more information from it. I love it. Even if you think it's old, from 2018, it is so good. It's so good. If you think of it, all this energy is not created or destroyed in the universe. There's a fixed amount. It only changes form from usable to unusable. Entropy increases. Unusable energy, entropy. Those are two of the laws of thermodynamics, right? Energy isn't created nor destroyed. It's only transferred from one form to another, and entropy or unusable energy forever will increase. All energy we're ever talking about on this earth, in our bodies, everywhere, is dependent on the sun. Energy from the sun, ultimately. Like, where'd you get the energy to run that triathlon? From the sun. Where'd you get the energy for those bicep curls? From the sun. Like, that's just so wild, right? And so there are many transfers of that energy before we get it, and we have to transfer it. The part of our body that's necessary to transfer that energy ultimately to oxygen, being the final electron acceptor, it happens in our mitochondria.
Mm-hmm.
I probably jumped the ship a little bit with going from oxygen to mitochondria already.
No, I think that's a good point, because, you know, we do all these tests, right? We do VO2 max tests, we do threshold tests, we do all of these different things, and we're always trying to either detect, you know, like, say, maximal oxygen consumption, the maximal rate of oxygen consumption that your body can do during high intensity exercise. Okay, well, where is oxygen actually being used? I can't say it's for sure 100%.
I don't think it's 100, but the majority.
Yeah.
For sure, the majority of oxygen utilization, especially during exercise, is going to be mitochondrial use.
Yep. It's going to
now,
be
in
within the
resting
mitochondria.
conditions, that probably changes a little bit, but not much, right? Still, mitochondria is going to be the primary site of oxygen utilization.
But, I mean, I would even argue, though, that oxygen utilization is still going to primarily be at the mitochondria. It's just, is it in the skeletal muscle, or is it in a different tissue mitochondria? You know, that's the proportion is going to change. But during exercise, the majority of oxygen consumption is going to be at the mitochondria. And you know what happens when you consume oxygen? You turn it into water. So you breathe in oxygen, you breathe out CO2, and you breathe out water. Pretty crazy. Because oxygen is only really stable when it has two more electrons, exactly like what you were saying. So you either have it paired as O2, or you have it paired with two hydrogens, which bring along two electrons with it, so you have H2O. So that sets this chemical gradient, or this
I like to think of it as drinking through a straw. That provides the suction necessary to pull. It's almost like oxygen is pulling electrons towards it. It wants electrons. And it's almost like the force of sucking through a straw. Electrons are being drawn to oxygen from molecules that have those electrons that they can share, that they don't have the affinity or the attraction to those electrons as much as oxygen. Yeah, so oxygen literally kind of provides the gradient necessary to draw or pull those electrons to it.
Yep, and correct me if I'm wrong, but I'm pretty sure oxygen, just like a single oxygen, is like one of the strongest electron attractors.
Second most.
Okay.
I think fluorine is only above oxygen in its need for an electron. So its pull. So it's the element with the second strongest electronegativity or reduction potential.
Yep. And here's a hint for everybody: is we don't have a lot of fluorine in the atmosphere, so our mitochondria did not evolve to be able to utilize fluorine. It evolved to be able to utilize oxygen. And you know, so now we've kind of set the stage. Oxygen is this big electron attractor sucker,
yeah.
And it wants electrons. So how do we set up our system to be able to give electrons to oxygen without just being like, oh, I'm just going to take a hydrogen and smash it with, or two hydrogens, smash it with oxygen, and then get H2O? Our mitochondria are actually the source of actually being able to do this. So now if we take a step back, And we start to say, okay, well, what do we use to actually make energy? We use substrates from the foodstuffs that we eat. So we can have, carbohydrates, fats, and to a lesser extent proteins. But ultimately what happens is carbohydrates and fats are brought into the skeletal muscle, slightly different transport pathways, other things like that. But through a process of breaking apart those molecules, breaking off carbons and transferring electrons, we are actually able to transfer those electrons to molecules that want to hold on to electrons, but not as strongly as oxygen. And these molecules are FAD, which you'll see in electron transfer flavoprotein, which is a very, very kind of obscure reference, probably for those of you who didn't study it in your PhD like I did, or complex 2 of the mitochondria, succinate dehydrogenase. You also, or most of those electrons are transferred to NAD. NAD is in the glycolytic pathway and is important for actually maintaining glycolytic flux. And it's also many times within the TCA cycle. So as you oxidize your carbohydrates, as you oxidize your fats, you're making more and more NADH and FADH2.
And notice Phil said oxidize. The whole reason the term is the nomenclature is oxidized is because typically oxygen is the final electron acceptor. And so it's like, oxygen stole your electron. You've been oxidized. That's literally where oxidized came from, is because oxygen is so commonly the final electron acceptor that they've just like, well, it's been oxidized.
Yep. Yeah, that's hilarious. You've been oxidized. It means oxygen has stolen electrons away
by the
from
axis of oxidation.
By the axis of oxidation. Oh my gosh, so many good. I hope people like. We're gonna make shirts and shit for this. I want to make posters actually for the axis of oxidation, and we have like
That'd
me
be
and
cool.
you as standing as superheroes.
I really think that like graphs, figures of the axis of oxidation would be super interesting.
Mm-hmm. Yeah. Okay. So back on board. We get these reducing equivalents. That's kind of like the technical name for NADH and FADH2. And then what happens is NADH gets fed into complex 1 of the mitochondria. Electrons get pulled off of NADH so that it becomes NAD again. And in that process, those electrons get passed down the electron transfer system, eventually getting to oxygen, where they're paired with 2 hydrogens and 1 oxygen, make H2O. There's a number of different steps. There's complex 1 through 4 within that portion of it. And, and we can also do the same thing for FADH2. We can take 2 electrons off of it, pass those 2 electrons down to complex 4, and then complex 4 will pass those electrons to oxygen, making water.
Right.
It's like, okay.
And so as those electrons are getting passed, electrons are negative, right? And so they're going to attract things that are positive. Tend to be hydrogen. So hydrogen's being produced through glycolysis, some of them are shuttled in to the mitochondria. They wanna go down the electron journey with the electron, right? Because negative, positive charge attracts.
Mm-hmm.
However, the mitochondria doesn't allow that.
Right.
There are 3 parts along the inner mitochondrial membrane that separates, that discouples. Well, maybe I shouldn't use couple. It divorces the transport of the electron and the proton,
mm-hmm.
and it moves the hydrogen just outside of this inner, very non-leaky, very the integrity is high in the inner mitochondrial membrane, separates a positive charge just outside and the negative charge with the movement of electrons just on the inside. And this creates allows the mitochondria to build capacitance, really. Now you have an electrochemical gradient called the protomotive force. And eventually, so you have the reduction gradient, oxygen's trying to pull the electrons in. There's a certain energy gradient. I'm going to start losing people. I know it.
Here. Let me give it a shot.
Okay.
So
okay.
yeah. So what I was saying is that we're pulling these electrons all off of NADH, FADH2. In the process of pulling those electrons off, like you were saying, you get hydrogens that are also want to go with them. But we're like, no. We want those electrons to go down and eventually, be paired with oxygen to make water. But that doesn't really do anything for us, right? Oh, cool, you just made
that
water.
Doesn't allow us to do work, right?
Right.
That's just electrons moving down their reduction gradient. And,
Right.
And we wouldn't be able to use that. We have to harness that need that oxygen has for the electrons.
Yep. So what we do at complex 1, 3, and 4 is we pump, by taking off those electrons, we pump hydrogens into the inner membrane space of the mitochondria. So the mitochondria, if for those of you that are unfamiliar, the anatomy is kind of unique. It's got an outer membrane, which is semi-porous, is able to, transfer things in and out. Essentially it has the same sort of makeup as the cytosol in a sense, or the inner fluid of the muscle.
Especially with smaller molecules and things. Bigger proteins can't pass, but yeah, the smaller stuff.
Yep. And then you have an inner mitochondrial membrane, which, like you were saying, is super tight. It's super the only tight. Yeah, super tight.
I was like, it's the opposite of porous.
It's super tight. So things aren't getting in and out unless you're transporting them across. Another wrinkle in this, it's like literally a wrinkle, is you have these invaginations. That's the technical term, but you have these pockets that are sealed off at the top, kind of like you can think about them as like a water balloon with membrane all around them.
They're sealed at the top. I don't think I knew that.
Yeah, so there's
Cristae are sealed at the top, huh?
Yeah, so there's I can't remember the exact, like it's a ton of protein complexes and stuff, but essentially it acts as like a cinch to keep everything in, right? Because if there wasn't one, then you just have hydrogens go floating off into nowhere.
I don't know. I'm not sure.
So
I need to look at the
within the Cristae,
review the structure again.
So these water balloons are called Cristae. And within the Cristae, that's where you get your complex 1, 2, 3, 4, complex 5, which we'll talk about in a little bit. But you get the ability to transfer electrons down that system, and in the process, you're pumping hydrogens into the Cristae. The big problem is that hydrogens are positively charged. They don't want to be close to each other. So you get all of these positively charged molecules together, and eventually, if you pump enough, they start slipping through, the cracks and stuff like that. It's not 100% important right now, but eventually they will start doing that. So now you have an electrochemical gradient, pulling the electrons down to be able to pump the hydrogens into the Cristae. Those hydrogens are building up, and they're making what we're calling a proton motive force. Those positive hydrogens want to get away from each other. And then, this is where like the coolest portion of, I think, like the mitochondria actually occurs. We have another protein called complex 5, or ATP synthase, that controls, kind of like a turnstile. If you're going into a fair or something like that, people are being counted as they walk in. It controls hydrogens going from the Cristae, where there's a ton of them, packed together, back into the mitochondrial matrix, which doesn't have very many hydrogens. So, and in so doing, by letting one hydrogen in, the protein itself, and you can actually look this up on YouTube, actually mechanically will turn every single time one hydrogen is placed or it goes through it. So it's actually a mechanical lever, like a turnstile, and then it uses that mechanical energy to actually take an ADP, so an adenosine diphosphate, an inorganic phosphate, and smash them together to make ATP. ATP should kind of be ringing a bell for a lot of people because that is the energy molecule of our cell. And in that way, that is why the mitochondria are the powerhouse of the cell, because they harness all of this energy transduction going from electrochemical gradient to proton motive force to mechanical energy, smashing ADP and inorganic phosphate together to make ATP. Frickin' sweet. So why do we care about that, though? It's like, cool, you just made energy, whatever. Every time you have a muscle contract, you're using ATP. So every muscle contraction, I'm waving my hands around during this podcast, when I go running, when I'm exercising, all this sort of stuff requires ATP to be available within the cell. So you have to have systems in place in order to make enough ATP in order for contraction to continue to occur. If you were to run out of ATP, you would look like a dead body. Like you would actually
look like you have rigor.
You would have rigor. You would, like, if you've ever, seen an animal or like roadkill or anything like that, they're stiff, right? And that's because you need ATP for the process of myosin actin cross-bridge.
I'm glad you said roadkill.
Cycling.
I'm glad you said, if you've ever seen a dead body, they're stiff.
Yeah. I've never seen a dead body. So.
I'm glad you said roadkill.
Yeah. Whew. Dodged the bullet on that one. But yeah, so that is kind of the basis for why oxygen is so important. But then the next question might be, okay, well, for those of us who are a little bit more learned in bioenergetics, but we have 3 energetic systems, right? We have our phosphocreatine system, we have our glycolytic system, and we have our oxidative phosphorylation. Why then is oxygen still so important when we have 2 other systems that could just make ATP for us?
Oh, you're asking me?
Yeah, I'm passing it over to you.
So some people may say that we do have 3 energetic systems, or some may say we have 1 energetic system with 2 that support it.
Mm-hmm. Ooh.
So the phosphagen system and glycolysis are accessory systems that kind of account for not insufficiencies that allow us to utilize oxidative phosphorylation to its full potential, actually. I'd say that. So there's the phosphagen system, and the phosphagen system is actually several reactions, but you tend to discuss the primary reaction is catalyzed by creatine kinase, and it is an equilibrium reaction where you have ADP and inorganic phosphate on your left, and you have ATP and ATP. Well, let me see. You have ADP,
creatine,
inorganic phosphate, and
phosphate,
hydrogen on your left, and then you have ATP and phosphocreatine on your right.
No, it'd be phosphocreatine, ADP on one side, and then it would be
right.
On the other side. It would be
right.
creatine and
creatine
ATP.
and ATP. Right.
Yeah.
Yes.
So yeah.
And
so okay.
Carried out in equilibrium. I used to think that the ATP that was being produced in the mitochondria would then diffuse out and was directly used to satisfy the need for ATP. At least in skeletal muscle, that's not the case. Most immediate ATP needs are supplied directly with phosphocreatine being hydrolyzed to produce ATP, and then also producing that unphosphorylated creatine that Phil just corrected me on.
Mm-hmm.
And then the ATP that is being produced in the mitochondria is used to rephosphorylate that dephosphorylated creatine. So there's a phosphocreatine shuttle where you actually have the creatine that is being used to provide the immediate ATP needs across the sarcoplasm within the muscle cell, is shuttled into the intermitochondrial membrane space where there's mitochondrial specific isoform of creatine kinase, and there mitochondrial ATP then rephosphorylates creatine and is shuttled back out. So creatine kinase portion of the phosphagen system is really kind of like a credit card.
Yeah, I was gonna say. So yeah, that the way that Sean Newsom describes it is it's the savings account.
Yeah.
Right. Credit card savings account is you have a certain amount of phosphocreatine within your muscle. And one thing
he calls it a savings account because we don't store a lot of mitochondria. If we did, the urge to hydrolyze is too great, and if we had too much ATP, we'd hydrolyze it. There'd be a quick energy release, and we'd die of hyperthermia. So that's why we don't have a lot of ATP stored.
Yeah.
And so instead of storing ATP, the phosphocreatine is a larger storage of this immediate energy. Mm-hmm. So totally, I see how that could be a savings account.
Yeah. So for those of you that are unfamiliar with this, so we just said ATP is like the energy currency of the cell. But the problem is we don't store a lot of ATP within the muscle, within the mitochondria. There's a very, very small amount of ATP that's ever stored just as ATP for reasons that you just said. So what we do is we're able to store phosphate groups on creatine, and then based on mass balance and other things like that, equilibrium reactions, as soon as there is an increase in ADP, so adenosine diphosphate, which would probably occur when you started to contract your muscles, right? Because you're going to be breaking down ATP. You have a little bit of ATP still in the cell, so you can start to do these contractions, but then you get a massive influx or a massive upregulation of ADP within the cell. Your borrowing system, your phosphocreatine, is going to be immediately engaged because there's no reactions that really need to happen. It's just, ADP goes up. I'm going to take these phosphate groups away from creatine. I'm going to put them back on to ADP. We're going to have more ATP for that contraction to occur.
Like whack-a-mole.
Like whack-a-mole, yeah. It's
as soon as that little whatever groundhog pops up, phosphocreatine is used to produce ATP so that we maintain our very small ATP stores in the cell.
Yep. And it should be noted, too, that even in like the most trained athletes, mitochondrial volume density only gets up to like 12%?
Maybe 15 or 20. I don't know. We often don't get muscle biopsies from the most elite athletes, right? And so that my modeling of the sub 2 hour marathon carbohydrate needs kind of opened my eyes to, I wonder what the mitochondrial density is in some of these elite athletes.
Yeah.
But we think that 12 to maybe 15% is somewhat of an upper limit. Now, could it be higher than that? Sure, but they're probably anomalies.
Yeah. And so the point there, though, is that because we don't have an inordinate amount of mitochondria, we still have contractile proteins and other things like that need to make up our muscle. Phosphocreatine is much more readily available at the site of contraction versus having the mitochondria be super integrated right next to the site of contraction or the breakdown of that ATP. So we need phosphocreatine, we need that savings account to be distributed within the muscle cell in order to provide ATP immediately. And then what happens is the creatine through creatine kinase gets rephosphorylated, and then it's kind of this transfer back and forth. So the oxidative phosphorylation system, or the mitochondria using oxygen, is kind of repaying or refilling that bank account as it's continually going lower and lower. And I would say that that's essentially the role of glycolysis as well, is to rephosphorylate our creatine or our phosphocreatine, and then the phosphocreatine really can do its job by being like a phosphate transporter within the cell. And
it's also kind of like the second parachute in a way.
Right.
Right? It's if there's a mitochondrial inability to maintain the ATP production necessary to maintain the phosphocreatine pools throughout the cell, glycolysis helps. Glycolysis can produce some substrate level ATP quicker than mitochondria can.
Mm-hmm. Yeah. So this, I'm sure for a lot of us, this is going to be a huge paradigm shift in the way we actually think about bioenergetics, because, you know, growing up, right, you see the graph. It's like, okay, for the first 10 seconds, you get, you know, phosphocreatine. For the next, I don't know, 30 seconds to two or 3 minutes, you're using primarily glycolysis. And then after that, you're using primarily mitochondrial oxidative phosphorylation. That's not the case. You need all of them acting at the same time. And the real sort of thing that is happening is, you know, you have your, I can't remember what you called it earlier, but you have, you know, kind of like your ATP provider, and then you have the things that are refilling that ATP. So you have your phosphocreatine, which is arguably, you know, this puts a lot more emphasis on the importance of phosphocreatine, but then you have the other two that are going to, you know, essentially be working full bore to try to rephosphorylate that phosphocreatine. And another reason why we don't just have, you know, say inorganic phosphate just floating around is because inorganic phosphate's also super reactive to stuff. It's got a negative charge, so it wants to bind to other things.
Like calcium.
Calcium is a positively charged molecule. If you have a negative and a positively charged molecule get close, then they're going to start binding together, and then that's going to result in an inability to maintain our calcium stores. Calcium stores are important for contraction to actually occur. We won't go into actual, you know, cross-bridge cycling theory and other things like that, because I think we've already probably lost, you know, 99.9% of people. But this is like the sort of shit that gets me super excited. So we've kind of established now, right?
Wait. Before you go on, you know what's so cool that you just made me think of? If we did have like 35 to 50% of the cell made up of mitochondria, there may not be so much of a need for phosphocreatine, but what we would lose is the ability to generate force. I wonder in species like in a hummingbird that does have around 35% mitochondria, I wonder if there's a difference in their creatine pools. I wonder if they have creatine pools.
I wonder, well,
Very
that,
interesting.
and then on top of it, you know, it's always a trade-off, right? You know, you need contractile proteins to generate force, but then you need mitochondria and other things to generate the energy
to transfer energy.
That force.
Yep.
So, you know, there's probably, you know, a bell curve of optimal. It's the same thing with cross-bridge cycling, right? There's an optimal overlap that's going to cause that. There's an optimal range of temperatures. There's an optimal range of pH, exactly. And it's like, you know, so our goal is to optimize whatever it is. And I would say that most likely, you know, like there's probably like an upper limit, and then other things start to happen where, you know, you start to maybe shift like the proximity of these different things. And, you know, with like those super high level athletes, they might not need, or they might not be able to have as much phosphocreatine around because they just don't need it as much, because you know, their mitochondria are so close to their contractile proteins that ATP that's being produced is so quick that it's, you know, you can have a really small savings account if you have the ability to replace that money very, very fast.
Yeah, so now I have a question.
Let's go.
As one trains, like goes through endurance training, becomes more fit, increases the density of mitochondria in the cell, what happens to creatine concentration in the cell?
I actually don't know.
How do creatine concentrations change with training?
Yeah.
I don't know either. Why don't we know this, right? It's so intimately related to bioenergetics and
we know
mitochondrial
how
respiration
glycogen changes, right?
Right.
Like the ability to store glycogen as long as you're fueling properly goes up.
Sure.
With training.
I don't know if creatine does.
Yeah, is creatine, is it more like static or
Right.
is it fluctuating? Like,
and if it is static, can you sample individual creatine concentrations in muscle and use that as a surrogate for the ability for one to expand their mitochondrial populations? Because there needs to be some marriage between the creatine pool in the muscle and the amount of mitochondria.
I wonder if it's one of those things where it's kind of inversely related. It's like, you most likely start out with kind of higher creatine phosphate,
right,
with lower mitochondria, and then as your mitochondria get bigger, there's probably some level of feedback mechanisms that are going on that are down regulating phosphocreatine, but continue up. And maybe it happens with PGC1 alpha, right? Maybe that is one of the, because we know PGC1 alpha or other portions affect, like the mTOR pathways. I don't know how creatine kinase is related to the other pathways, but we for sure see, going back to glycogen, we for sure see upregulations in glycolysis with high intensity interval training. And I believe we actually saw increases to creatine kinase as well. So maybe it's another one of those like function structure sort of things where, because structure takes longer to build and it's a little bit easier, right? If there's only one step in creatine kinase or in the creatine kinase reaction, maybe it's easier to upregulate creatine kinase in the beginning. And then as you get more fit, creatine kinase might stabilize as mitochondrial volume density and mitochondrial function start to get bigger and better. Because it's this idea of symmorphosis that we were talking about, right? So again, for those of you who don't know that word, it's that the human body or other things like that is built only to have enough of whatever it is around. You don't have excess, essentially. And that's, I mean, even this theory is a little bit, iffy sometimes, right? With people coming out and saying, oh, well, mitochondrial capacity is 2 times bigger than what we can actually deliver. In trained athletes, it's probably not 2 times, right? It's
I want to do we should calculate it out, because I actually calculated, I think actually I'm not ready to say what I'm about to say yet for public consumption.
Yeah. You guys can comment down below if you think you know what he was going to say. I can almost guarantee you don't, because I don't even know what he was going to say. But
I'm
it's
surprising you, because I'm changing some of my long-held opinions, huh?
Yeah. But it's interesting, and I think that's important, right? Is when you read things and you understand things more, it's like, okay, you can change your opinion. You're allowed to do that. I'm giving everybody the ability to change your opinion. And it's like,
I do it all the time.
We just dropped this bomb on you that creatine phosphate or phosphocreatine is actually really important, within the bioenergetic systems, not just at 30 seconds, but for extended periods of time. And it's this relationship between the ability to have enough ATP available and then rephosphorylate creatine in order to then make more ATP available. So you need both high levels of mitochondrial volume and mitochondrial function in order to use that oxygen, pull those electrons down the electrochemical gradient, sequester protons into the cristae, transport, or to have facilitated transport of the protons back through ATP synthase to resynthesize ATP. That's then going to interact with creatine kinase within the mitochondria, which is then going to interact with creatine kinase in the sarcolemma. sarcoplasm, not the sarcolemma. And, it's much more complicated in terms of the amount of steps. It's not just like, oh, ATP just diffuses into nothingness and then gets to the myosin head and then can, be hydrolyzed again. And then we also have to add on, okay, well, where the hell does glycolysis come in here? Glycolysis is kind of doing the same thing, right? Glycolysis is supplying ATP, 2 ATP per breakdown, right? Something along those lines. That ATP could be used for rephosphorylation of phosphocreatine, or if it is in close proximity to the myosin actin sites, there's no discrimination. If you need energy, you gotta have the ATP to do it. And then on top of that, we're sending high energy molecules into the mitochondria to be further oxidized to generate more NADH, more FADH2, and then that can then further be used for more ATP production within the mitochondria. So all which would not occur if we did not have oxygen pulling on that electrochemical gradient to begin with. Because if you didn't have enough ATP being created from the mitochondria, you wouldn't be able to rephosphorylate phosphocreatine. If you didn't have enough phosphocreatine, you wouldn't be able to have contraction, and you'd just be done. So, again, that's kind of where we started and where we're at. But I think like this, it's important to understand all of this, because then you can start to say, okay, well, maybe not all, or maybe, a specific type of training isn't just one thing or the other. It's not just phosphocreatine or oxidative phosphorylation. It's actually a mixture. So then you can start to understand why we have these adaptations, like in my high intensity interval training study, where we showed that people's mitochondrial function increased 30% in a week with no visible changes to mitochondrial volume density or other things like that. And there probably was starting to be accumulation of proteins. We just don't have the ability to detect it. But it starts to lend credence to this idea that when somebody is telling you on the internets, oh, zone 2 training is the only way you can increase your mitochondrial function or your mitochondrial volume density or whatever it is, you say, whoa. If I'm doing zone 2 training, let's think about this for a second. Zone 2 training, from now our new understanding of bioenergetics, is still going to be heavily stimulating our mitochondria. If we're heavily stimulating our mitochondria, there's going to be room for adaptation and need for adaptation for that, but it's also going to be stimulating glycolysis and phosphocreatine all at the same time. So you're probably going to be getting adaptations that are not just mitochondrial volume density, but maybe a little bit of adaptation to glycolysis, maybe a little bit of adaptation to the phosphocreatine system. And then you say, okay, well, now we're doing high-intensity interval training. High-intensity interval training hits, or at least what we would have thought is like, oh, only hitting, glycolysis and phosphocreatine. It's like, no. Now we know it's hitting the mitochondria too. So it makes
Big
sense.
time.
Yeah, that mitochondrial function would then be stimulated to increase. And maybe there is some expansion of mitochondrial volume density. So it's not this like black and white, sort of thing, like we want to pit bioenergetics to everybody, back and forth. Granted, it does take a little bit more mental energy to try to understand bioenergetics and then the adaptation, the adaptive response that's actually happening. But to say, this is the only thing you can do to get this adaptation is totally off base, because you're stimulating all bioenergetic pathways at all times during any type of exercise. It's just the types and amount of stimulus and adaptation that's actually going to be occurring is going to be occurring based on, all of those, the 7 homeostatic, maybe 8 homeostatic perturbations that we will talk about in another podcast, because this is just laying the groundwork for, oxygen being important as the most important molecule. So that was a little bit of my soapbox, but I'll let you. What are your thoughts?
Yeah, your energy systems don't know if you're getting up to get a banana or getting up to run away from a grizzly bear. And so anytime ATP is utilized, all energetic systems are initiated collectively together to produce as much ATP as fast as we need it. Mm-hmm. And so it's just that the immediacy of having phosphocreatine stores and the quickness in which glycolysis can produce ATP, they're more immediate or faster means of producing ATP until we've revved up mitochondrial respiration, producing ATP as high as it can. However, that is a limited speed too. That's why we can't maintain our sprint speed indefinitely, right? And so what is ultimately setting your ability to maintain a certain pace is ultimately comes down to how fast can you produce ATP.
Right.
And you're not going to run a marathon growing your phosphocreatine stores or even expanding glycolysis because they're so limited in their capacity to produce ATP. You have to expand your mitochondria. You have to add, think of mitochondria as like cylinders in a gas combustion engine.
If you add more cylinders, you're going to be faster. You're going to make your engine bigger.
Yeah, exactly.
Whereas if you could add high octane fuel, but again, right? That's
carbohydrates versus fat.
Yeah. And that's going to be a burst of energy. But ultimately, what's going to limit your ability to maintain high levels of ATP production or ATP resynthesis is how well your mitochondria can actually generate that ATP, because you'll run out of glycogen at some point. Your ability to rephosphorylate phosphocreatine is going to be diminished, and so that gets in kind of the to the weeds of fatigue and other things like that. And I don't know if I'm ready to dive into that on this podcast episode, but yeah, that is so important to think about. And the good news is that whether you're doing low intensity, high volume training or high intensity interval training or sprint interval training, you're going to get some level of stimulus to your mitochondria. Optimally, though, you want to do both. You want to do zone 2 training in order to get the volume in, because we know volume preferentially upregulates mitochondrial volume density, capillary density, so both the ability to to deliver oxygen and then get that oxygen into the mitochondria. So that's going to give you a better ability of the transfer of oxygen. And then high-intensity interval training is going to give you the ability to actually utilize that oxygen better, because it gives you more, or it preferentially upregulates the complex 1, complex 2, all of those complexes that are necessary for electron transfer down the electron transport system, ATP resynthesis, and it also makes more folds within your mitochondria so you can sequester more hydrogens. Why is sequestering more hydrogens good? Because I just said we're not going to go to the fatigue thing. But it builds capacitance, but it allows you to buffer more hydrogens so that you...
that as well. Yeah.
Right? It allows you to buffer more hydrogen so that you don't have to rely on your blood buffering capacity for hydrogens. And anyone who wants to challenge that notion, please call me out on it, because I've argued this with a lot of people, and they're like, there's no way that the mitochondria actually are involved in fatigue reduction. It's like, no, they are, because they buffer hydrogens.
Well, and they are a user of inorganic phosphate.
Right.
So the oxidative phosphorylation uses inorganic phosphate and uses hydrogens, the two things that initiate fatigue within the cell.
Yep. And
how can it not?
The more oxygen you're actually using, the more oxygen you're buffering onto hydrogens. Yeah. Or onto oxygen, excuse me. So you're taking hydrogens and putting them onto water.
Yeah.
Water is not acidic, so you're essentially buffering, by using more oxygen as well.
Yep.
So it's this multifold benefits of having very high mitochondrial volume density as well as high mitochondrial function, because again, for all those reasons I just listed, is you're going to have better ability to sequester hydrogens, you're going to have a better ability to use oxygen, reduce oxygen to water, you're going to have a better ability to use inorganic phosphates, which you're going to slam back onto ADP to make more ATP, which is then the energy currency of the cell, which is then going to be able to be used eventually at the myosin head for cross-bridge cycling, which is actually what's going to allow you to maintain force output. So, yeah, it all it starts with a myosin actin interaction, but but the next step then, right, is your ability to actually utilize oxygen and how much can you actually use. And the last thing I guess we can talk about, because this was super interesting to me, is that if you're thinking about, like your distribution of energy systems within your cell, right? You have your phosphocreatine, you have your glycolysis, which kind of links, your cytosolic energy production with your mitochondrial energy production. Then you have the mitochondria. And something that was said in this research paper was that what our cells are trying to do is essentially come back to homeostasis as quickly as possible. Like that's what our cells are reacting to, is a disbalance or something that's getting messed up, and
at
it's
all
trying
times.
at all times.
It's like,
and we're trying to rebalance it, right?
Yeah.
So it's like it's this constant teeter-totter effect.
Yep.
And we're trying to get better and better at it, but it's always happening. So something that was said was that if you have higher phosphocreatine but lower mitochondrial volume density, you're actually going to be able to reestablish homeostasis within the cell faster. I texted you that. I was like, what the hell? Like that just seems totally, like we just talked about how important big mitochondria are, big functional mitochondria and all this other stuff. And you're like, well, yes, you'd be able to reestablish homeostasis, but you're also going to accelerate fatigue faster.
Totally. And that's how is written like by a biochemist or a chemist. They say you reach equilibrium quicker, but that also means like if your max on a VO2 max test is 150 versus 300, you're gonna hit that quicker, right? And that's the equivalent of what's being said. And so
right.
It sounds like, reaching a steady state metabolism, that's good. Not if it's so low, because if you
right.
can only maintain steady state metabolism at low metabolic demand, you're going to be probably suffering from chronic diseases.
Mm-hmm.
And so it is a weird way of stating it, but that because when I read it, I'm very much reminded how much I am a physiologist. I want to be a biochemist. This is awesome. And studying mitochondria, you have to understand these concepts to a certain degree. But yeah.
Because that was a paradox to me. I was like, what the hell? Like, that doesn't make sense. But then that got us kind of on this discussion of, well, as an endurance athlete then, right, your first and foremost thing should be trying to develop capillary density and mitochondrial volume density. I think, I say mitochondrial volume density, but mitochondrial volume density and function.
I was just trying to do it. I'm trying to do it.
You're just thinking about it. I thought you were just going to get mad and be like, no, that is the first thing I disagree with you on.
No, I'm trying to do it.
Yeah. So capillary density within your muscles, and then mitochondrial volume density and function. Because you can have a ton of mitochondria, but if they don't have, very well packed in Cristae and complexes and supercomplexes and other things like that, you're not going to be able to utilize all that oxygen that's actually coming to you, right? So that should be first and foremost. But then we started talking about, well, okay, if you have large mitochondria, would it also be beneficial to then be supplementing with creatine? Because we know that supplementation with creatine actually allows for higher stores of creatine within the muscle. I know this is actually a controversial topic for endurance athletes, because along with more phosphocreatine, you get more water stored within the muscle, which then is seen as potentially bad because, that's more weight. You could potentially gain a little bit of weight. But I would say that that's most likely beneficial weight, and especially if you're training with creatine for extended periods of time, then your body is going to get used to that extra weight, and it's not that much. Unless you're really depleted.
What if I told you I could put on 20 pounds and be faster than I am now?
It's like, yeah, sign me up.
Just muscle. If it's just muscle, guess what? You can. If you just add muscle, I couldn't add just 20 pounds of muscle. I probably can't even add just 2 pounds of muscle. Actually, probably not even just one. But it's good weight. And also something that's not talked about is not only does the creatine give you kind of that that larger savings account that Dr. Newsom was talking about in bioenergetics.
Mm-hmm.
But oh shit, what was I gonna say?
You lost it. Oh,
I
no.
totally lost it.
So what I would say though is like, okay, like the research that has been looked at has shown that endurance athletes who supplement with phosphocreatine, their performance doesn't go up.
Oh yeah.
And this might be from like short study design.
So you've read the research. There are studies that show that endurance performance doesn't change. What were their tests of endurance performance?
I know. So I can't remember, and I'm kicking myself right now because I should have grabbed there's a meta-analysis that actually like walks through everything, because they're suggesting like, oh, maybe you should be taking phosphocreatine because yes, it doesn't help your endurance performance, but it also doesn't hinder it. So whatever the test that they were doing, and I can't remember, I think they were, they weren't the best tests of endurance performance, but they did them nonetheless. It's not hindering your endurance performance with acute loading of of creatine. So that should be the number one thing. All these people are worried, I'm going to gain weight, I'm going to lose my performance, blah, 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 blah. No, right there. It doesn't show any decrement. But then I guess the secondary argument is like, well, if it's not improving my performance, then why would I take it? So less overall deviations in homeostasis. So less stress felt on the body per the same exercise load. You're able to recover faster. And if you are somebody who is training a lot, being able to recover faster is actually indicative of being able to do more workouts more often. Talk about consistency, right? With consistency, you then be able to build more volume and other things like that. I think, though, what we do need to just be aware of is like, okay, well, if you're supplementing with anything, if it blunts some of the stress to the adaptation, then most likely you might be missing out on some of those adaptations. It's like if you take high levels of vitamin C or vitamin E immediately before and following a training sessions, you actually see blunting of some of the responses that would be indicative of improvements in performance. So you just have to be aware of that. But it helps with sprint capability. It helps with repeated work bouts. It helps with all of these different things. If you're low on it, it helps with cognitive function. So
there's more and more research coming out. That's actually the main reason why I really want to start taking it. And what I was going to say is you say that it increases hydration of the muscle because you increase the osmolality within the cell, pulls water in. Well, that alters the relationship, the distance between the myosin and the actin filaments. And so actually cross-bridge formation, there's evidence to show that leverage, that cross-bridge, you get better leverage so you can get a little bit more force per cross-bridge formed. So not all the increased force production with creatine supplementation comes just from having this increased phosphocreatine pool. Yeah, exactly.
Yeah. So and it's something like, I don't take specifically creatine, but I do take, it's called like, it's mass gainer. So it's essentially just a bunch of maltodextrin with other things mixed in, like protein and some creatine stuff and some other things like that. And I think, first of all, I haven't seen a decrement in performance or other things like that. And when I have taken creatine in the past, haven't had any decrements in performance. So that's always the thing I'm looking for, is like, is this thing negatively affecting the true outcome of what I'm trying to do, which is the performance that I'm trying to have. And then the other thing is that, creatine is arguably one of the most looked at nutritional supplements on the market. So if you have a good creatine that's, not tainted with other shit, like, it's one of the safest, one of the most researched supplements on the market, and there are tons and tons of benefits, potential benefits to it. You do have to be careful about, taking too much of it in the beginning. You don't have to load with 20 grams of creatine anymore. You just need to take, I think it's about 5 grams. there's a Huberman Reddit thread that I was reading today where people were talking about like 10 grams a day.
I've heard 5. I've even heard like 2 to 5.
Yeah. So the big thing you have to watch out for is gastrointestinal distress, just like with anything. If you do get issues with your stomach with it, then break that up into 2 grams 3 times a day, 2-2-1. And that seems to make those issues go away. Dang it. I really want to, I'll pull back up that meta-analysis at some point. We can talk about it on the next podcast episode. But I think what we're trying to get at is that it doesn't seem like there's much decrement, to taking phosphocreatine. If anything, it's going to, help with recovery, help with other things like that. And yeah, so.
Well, totally. And now I'm wondering if the phosphocreatine pool doesn't change and somebody continually increases their mitochondria, then they're going to be limited by their phosphocreatine stores.
Mm-hmm. Well, yeah, and I think too. I wonder, because it would be a matter of being able to dephosphorylate and rephosphorylate phosphocreatine. That's essentially what you're talking about. So if you have more mitochondria, then you can essentially rephosphorylate that phosphocreatine or that creatine faster.
Right.
And then you can have that transfer happen faster. So that would be one of the benefits, right, of just having more mitochondria. But then if you expand that phosphocreatine pool as well, you start with a larger savings account. So you actually don't have to talk. This could be like the idea of a little bit more of like that glycogen sparing, right? And one of the reasons why, because you could focus on slower mitochondria that could oxidize fat longer, replacing phosphocreatine for longer because it's got a larger pool. And then maybe that's one of the reasons why we start to see that shift in carbohydrate oxidation occur later and later within it's just less of a stress, right?
I wonder if that has something to do with durability. Because if you're running for hours, like exercise, when you go into the doctor, say you're going in because you had chest pains and they took your blood and they saw that you had an increase in creatine kinase in your blood, they'd be like, ooh, you may be having a heart attack. If you worked out, you'd be like, well, I just worked out. You can have spikes in creatine kinase. If you're having spikes in creatine kinase coming out the muscle, then you're most definitely having creatine as well. I wonder how much creatine one can lose, like over the duration of a marathon or something. Yeah. Right?
That's a really good point. That's not something, and it's kind of the same thing with like iron supplementation for runners, where, if you're pounding all the time, there's like actually some level of degradation that happens within your feet that actually blow up, essentially like blow apart erythrocytes, which are red blood cells. Yep. So then you lose iron in that case. So I wonder if it's kind of the same way. It's like you're damaging your muscles to such an extent, you eventually lose phosphocreatine. And then if you're not replacing it by eating enough red meat or supplementing with, because really, it's really hard to get it from anywhere other than, I think, red meat. I think that is
Isn't chicken a good source? I don't know.
Be, but
I've just heard this. I have no idea.
I'm pretty sure it's like animal-based protein is like where you get it. So
muscle,
that could be
from
poultry.
Muscle.
Exactly. Yeah. You get what you're eating. So this is where vegetarians and vegans who have been placed on creatine supplementation have actually found enormous benefits. And for the most part, I would say most of the time with supplementation, you stand to make the most benefits if you're already deficient in something. So take that with a grain of salt. But yeah, so that is interesting to think about. If we're constantly doing a lot of high damage exercise, running being one of them.
Eccentric, that has that eccentric component to it.
Yeah. then maybe that's just another reason why, as a runner, you might want to supplement with creatine to replace it. But again, it's like I don't know all. If any of you know an expert on creatine who would want to come on the podcast, point them out to me, tag me, or tag them in this post, or send me their information or anything like that, because I would love to talk to somebody about creatine. And I think it's been relegated to like the bodybuilding community just because it has been shown to improve force output and other things like that. That's another thing. Okay, so if you're improving your ability to generate force, then say with squats, say your max squat goes from 200 to 400 pounds. The force, and then you go and you run at 200 pounds of force. You essentially just went from 100% to 50% of your max force output. That's going to be much less of a stress on your on your muscles than it was when it was 100%. So you're not going to release as much epinephrine, norepinephrine in response to that same exercise intensity, It's not going to vasoconstrict your adipose tissue as much. It's not going to cause shifts from that massive release in stress hormones. So it's, there maybe that has been one of my contentions for a long time as to why strength training is actually so beneficial, is because it raises your maximal force output. So then when you're running or cycling, that percentage of contraction, based on your muscle strength, is actually lower. So it's just less of a stress, by getting stronger.
Yep. I also think that it really probably improves force transduction down the muscle. I bet more than endurance training itself.
The strength training or the phosphocreatine?
Strength training, I think, probably improves force transduction down the muscle as well.
Well, yeah, because I think, you have to think about, the ability to coordinate, the firing, all those motor units and other things like that. And this is like that neuromuscular stimulus, right, that you would get that. Unless you're doing like all-out sprints or plyometrics or other things like that, you're not really ever getting that with endurance-style training. So I agree with that too. I think there's in the beginning stages neuromuscular components to it, and then in the as you get more trained with it, it's going to change maybe your pennation angle, and like just the way that your muscle is actually contracting. It's going to make it more efficient in terms of force transduction. So, cool. We'll leave you guys with that. I think that was a really cool discussion on oxygen being the most important molecule. And I hope we convinced you guys that that's the case. And if we didn't, let us know why you're not convinced. And I'll try to convince you, because I think it is the most important molecule. We focus purely on the muscle today, but we didn't even get into, oxygen transport, how, changes to oxygen or changes to other things like that could be signaling changes to breathing, changes to increases in stressors or stress and, hormones being released and other things like that. But I think that's another conversation for another day. You can always find me at Critical02 on Instagram. I'm going to start tagging Robby in all of our podcast posts and stuff like that. So go and give him a follow on Instagram. Ask him any questions that you have. We're always up for trying to answer questions for you guys. He's actually on Twitter or X. So if you want, to see his research and other things that are coming out, go follow him over there. If you're on YouTube, make sure to subscribe. If you're listening to this on Spotify as well, subscribe, and also give us a 5-star review if you're enjoying this sort of content. I know if you got to an hour and 13 minutes into this episode, you're probably enjoying it. So go give us a 5-star review. It really helps us out. And with that, Robby, you want to leave them with anything today?
Yeah. If you're thinking of hiring a personal trainer or a coach, ask them about lactic acid. Ask them the role of lactic acid in the biology of fatigue. And if they try to explain to you that lactic acid is the cause, don't hire them.
Boom.
Boom.
Words of wisdom from the eminent sage, Robby Jacobs himself. All right, guys. Until the next one, we'll see you guys later.